super duper important that you actually show this step. You're going to show the numerator is equal to 0, and you're going to show that the denominator is also equal to 0. Make sure you do this in limit notation, no shortcuts. This only takes about 12 seconds to do. Everybody, welcome to Cranky Calculus. We're going to talk about L'Hopital's rule, the Frenchman here. It's a super important rule in which helps us solve for limits. It really makes a lot of Unit 1 obsolete. So it's a really great shortcut that we do have, and we do need to know it. So before we get going here, make sure that you like and subscribe. I have too many non-subscribers watching this video. Make sure you subscribe, all right? What the heck are you waiting for? Subscribe now. Let's get into this. So pretty much what we're going to talk about here is if we have a limit that is in the form of 0 over 0, then we can use L'Hopital's rule, or if we're in the form of any type of infinity over infinity, we can use L'Hopital's rule. What it does is if we can find the derivative of the numerator and the derivative of the denominator and we get an actual answer, then we're good to go. Again, that only works if the original is in the form of 0 over 0. It's super important yet that you do not write equals 0 over 0. Common error. I see it way too often. I even saw it in the tests I was grading today. I'm very disappointed. Can't imagine why I'm so cranky. And I've said it 10,000 times, if not more. So let's go to this first limit right here. So it's important that we always do a mental plug into these limits, just as maybe these are evaluated super easily. So if we do cosine of 0, we get 1 minus 1. Numerator is 0. Denominator also, when you plug in a 0, plug in a 0, you get ln of 1, which is 0. It is super duper important that you actually show this step. So limit as x approaches 0. So you're going to show the numerator is equal to 0, and you're going to show that the denominator is also equal to 0. Make sure you do this in limit notation, no shortcuts. This only takes about 12 seconds to do. And that will earn you the point to start to go towards L'Hopital's rule. So because of this, I'm going to use LH. By the way, I call it LHOP. Hope you don't mind, and I really don't care if you do mind. Means we're going to find the derivative of the numerator now. So we're going to do the limit as x approaches 0. The derivative of the numerator is going to be negative sine of x. Derivative of the bottom for the ln is going to be 1 over x plus 1. And can I do a direct plug-in right now? Totally can. If I do a direct plug-in, now I don't need my limit here because I'm doing a direct plug-in. I'm going to get negative sine of 0, which is 0, all over 1 over 1, which is going to give me 0 over 1. So my answer here is 0. So I can find this limit. It is super important. I'm going to erase this in a moment. If you ever say that this equals 0 over 0, people, you're going to get it wrong. Do not do this. This is bad. Because what you're telling the grader is that 0 over 0 and 0 are the same thing. So you never want to say equals 0 over 0. You can put it in the form of 0 over 0, but does not equal 0 over 0. I tell my students to do this red box right here. I'll box it. I tell my students to do this red box. That is required. The blue is going to lose you points. Oh, sorry, you're not going to be able to earn points. Okay, so make sure that you do it correct. Okay, move on to the next problem. I had to change this one up a little bit. That's why it looks different. But don't worry, on the free notes that you get in the description, don't forget there are free notes. Everything is already fixed and looks good to go. So this is the problem that I want. It just looks better from what it was originally written. So again, we're going to use LHOP here. If we do have this in the form of 0 over 0, we plug in 0 in the numerator. I'm going to end up with 1 minus 0 minus 1, which is going to give me 0. So it's important to note that in this little area so that I can use LHOP. So e to the 3x minus 1 does equal 0. The denominator, when I substitute in a 0, also gives me 0, so I will be able to use LHOP here. So this is equal to, and I just put an LH, noting that I'm using LHOP, is equal to the limit as x approaches 0. On the denominator, I know I get 2x. Numerator, I'm going to get 3e to the 3x minus 3. Derivative of negative 1 is minus 1. So can I plug in a 0 now? No, I'm going to get 0 over 0. So I need to go ahead and go through and do LHOP one more time, hopefully. And actually, we can do LHOP as many times as we need. Should be an E right there. As many times as we need until we get a final answer. Sometimes if you do it more than twice, I've seen it do it 3 times, totally fine. Okay, so fine. After more than 3 times, then you're probably doing it the wrong way, and there's probably a better strategy other than LHOP. So now, using purple, so this is equal to the limit as x approaches 0 of 9e to the 3x all over 2. And now I can easily plug in a 0, and I'm going to end up with an answer of 9 over 2. And that is going to complete this problem here where we had to do LHOP 2 times. On this last problem here, we'll do this one in pink. We're going to look at the limit as x goes to 0 from the right of cotangent of x over ln of x. It's kind of important to know. You might want to know what these graphs look like, because if you don't know what cotangent looks like, you might not know what's going on. So if I were to just real quickly graph cotangent of x on an axis like this, cotangent of x is a decreasing function. That's probably not the best way for me to draw it. That's a better one. So as we look at 0 to the right, you can clearly tell that cotangent of x equals positive infinity. If I look at ln of x, hopefully you know what that one looks like. If you don't, oof, you're going to have some problems here. As we look at 0 to the right, we're actually going to get negative infinity. So because we are in the form of 0 over, or not 0 over 0, infinity over infinity with some type of positive or negative, we can use LHOP here. So I'm going to use LHOP. I'll box this up so we see what was going on. So this is going to be the limit as x approaches 0 to the right. Derivative of cotangent, hopefully you know what that is. That is going to be negative cosecant squared x. Although derivative of ln is 1 over x. Okay. Now, can you plug in zeros here? Not as written. And this is one of those where if you just keep doing LHOP, you're just going to keep cycling over and over again. Let's just rewrite what this limit is. I'm going to change this order around. And I know that cosecant actually produces a sign if it's in the denominator. So I'm going to go ahead and go negative sine squared of x in the denominator. And then since 1 over x is in the denominator, if I were to find the reciprocal of that, it's going to get x on the top. So these are completely equal ratios. That's why it's important to be good at algebra, so that you can recognize this and then rewrite it this way. You will get 0 over 0. A couple options. You can rewrite this again as LHOP. I won't, just because I do know my trig limits pretty well, and I'm going to skip that LHOP step that I really don't want to do, because I know that I can rewrite this as x over sine of x times 1 over, I'm going to put that negative. You don't mind. What do I care if you mind? Put that negative up top. This is mathematically equivalent, but I do know for my ratios now that this first ratio right here, I'll highlight it in gray, this first ratio right here is equal to 1. So I'm just looking at the next ratio, and if I were to plug in a 0, I would get negative 1 over 0. So this actually does not exist, because we cannot divide by 0. You could have easily done another LHOP at this step right here. You ended up finding the same results anyhow. Be careful for that one, you do have some chain rule, but you would have got the same result. We can't divide by 0, so this is going to be a DNE, and that is actually going to wrap up our video here. Do not forget to like and subscribe for more videos.